Number 1, identities of X, Y, and Z based on their melting points, boiling points, and density. First of all, we look at X. Melts at -7 degrees, boils at 59 degrees. So it will be a liquid at room temperature conditions. Liquid, we have between bromine and iodine. Okay, bromine will be the one that will be liquid. Iodine will be solid at room conditions. And then checking Y, rather low melting point and low density between sodium and magnesium. Sodium group 1 will be the one that has lower melting point, or low melting points and low density. That leaves us with magnesium for element Z. Number 2, redox reaction between lead-4 ions and bromide ions. So lead-4 will become lead-2 plus, bromide will become bromine gas. So we try to form an equation, okay, or bromine gas or bromine liquid. We try to form an equation where we have lead-4 plus gaining 2 electrons to form lead-2 plus. Bromide becoming bromine, it will lose 2 electrons. Before we merge these two equations together, we have to make sure the electrons are the same number. In this case, they are the same, so we can actually put them together for an overall equation that has 1 mole of lead-4 plus reacting with 2 moles of lead bromide. Now we have this info. We have to find out how many moles of lead-4 chloride did we use. 6.98 grams. We divide by mR of lead-4 chloride. That gives us 0.02 moles. Okay? And it's important that 1 mole of lead-4 chloride will actually give us 1 mole of lead-4. So 0.02 moles of lead-4 chloride was used. It will give us 0.02 moles of bromine. And then we multiply by the MR that we see from the periodic table. 79.9 multiplied by 2. That will give us the mass of bromine produced. 3.196 grams. Which of these 4 will have equal number of electron pairs and unpaired electrons? So same number of electron pairs, same number of unpaired electrons. So we can draw out the configuration based on the number of electrons: beryllium, carbon, nitrogen, oxygen. And then we look at the number of electron pairs, okay, within quantum shell 2. So we have 1 electron pair, 0 electron or 0 unpaired. So this is not what we want. 1 pair, 2 unpaired. 1 pair, 3 unpaired. 2 pairs, 2 unpaired. So same number of pair, 2 pairs and 2 unpaired. So D will be our answer. Number 4, the approximate angle between the bonds formed by the nitrogen atom. So we have nitrogen in here, and we try to find out the number of lone pairs that it still have. It has 5 electrons. 1, 2, 3 are used for bonding. So there are 2 more electrons that are not used for bonding, or rather 1 lone pair not used for bonding. So we have 2 bond pair and 1 lone pair. They will form approximately 120 degrees or even slightly lesser, because this one, the lone pair, requires a slightly larger space. Okay, but approximately they will take about 120 degrees angle from each other. Under what conditions will the behavior of chlorine become like an ideal gas? This is more of a recall question. Ideal gas, when the particles have high energy, high temperature, they move fast, and when low pressure allows them to be far apart, they will have negligible attraction to each other. So high temperature, low pressure conditions, we will approach ideal gas conditions. So low pressure will be 50, higher temperature will be 400. We have nitrogen broken from the fluorine atoms. This is the molecule NF3, and then this shows that it's broken all into separate atoms. So we have two molecules of NF3, 6 bonds are broken. Okay, 6 NF bonds are broken. So 6 multiplied by the bond energy of NF, that will be equal to the enthalpy change of the reaction. And if you want to find each bond energy, we will divide this by 6. Okay, and also recall that bond energy is to break bonds. It will be endothermic. It will come with a positive sign. Reaction of chlorine and hot sodium hydroxide. Checking the oxidation number of chlorine. In Cl2, it's an element, so it will be 0. NaCl, Na is +1, chlorine will be -1. That gives us C as the option already. We can check the last one. Sodium will be +1. Each oxygen will be -2, so this will be -6. So your chlorine here must be +5 to make it an overall 0. And that also confirms C. Number 8, sulfur dioxide. There are two reactions. Which statements about these two reactions is correct? We can check the issue of oxidizing and reducing first. Okay. We just use sulfur as the example. Sulfur here will be +4. Inside here will be +4. It is still +4 here. And finally, this will still be +4. So if you check the oxidation state of sulfur, you realize there's no change in the sulfur. In other words, it won't be acting as a reducing agent or oxidizing agent. Because if it is, its own oxidation number will be changing. So it's not a redox reaction. C, SO32- X as an acid. The species is here. You can see that it actually takes in a proton to go backwards. It's actually a proton acceptor. So if anything, it is a base. So that leaves us with option A, HSO3- X as a base. In this case, if you look at HSO3-, it can take in a proton and form SO2 and water, the backward direction. So in this case, it is acting as a proton acceptor. It is a base.